right? Good. Part C. They introduce a road. Ugh, jerks, okay, but that's all right. With the equation of path, it's very easy to work with, okay? So I'm going to make this a bit bigger because not enough room to show you what's going on. Okay, there's my road. Okay, so obviously once it hits that, it's not going to actually go through there. So this part of the graph no longer matters. Okay, the road is inclined from the horizontal at tan inverse of a fifth. That's a funny angle. The reason they picked that is just to make your numbers a little easier. Okay. Show that the ball is about 9 meters above the road when it reaches its greatest height. Required to prove. 9 meters above road. Sorry. There you go. Okay, now, how do I work this out? What does height represent in this equation? Okay, well, in the first place, you could just get height from this. Okay, you just get height from that because that's what y is about. Okay, but now that I have a road in the picture, the height is actually something like this. You know, it's this distance, right? Or this distance, or this distance. Okay. And the important thing you want to get is that it's very easy to work out that distance if you know how high this is and how high this is. Really easy, okay? I've got the equation of path, right? What's the equation of this thing? What should we call it? I guess you'd call it equation of road, wouldn't you? Equation of road. How do I work it out? I just want its gradient, don't I? How do you find the gradient of a straight line? It's tan theta, isn't it, right? Tan, and in this case, theta is this, right? Tan of tan inverse of a fifth. So your gradient is just a fifth. So therefore, here's the equation of road, right? Now therefore, if I want to know this distance, right, I just have to take away how high the ball is from how high the road is. That's all, okay? So, running out of space, I'm going to leave the equation of path there. That's all I need. Okay, so I've got this distance. This is the height above the road. Okay, and I want the greatest one. It's going to be this. Whoops. Minus this. There you go. That's the height at any given time. Okay. Now here's an important thing for you to notice. Okay. Because I've adjusted this, two things. If I were to graph this, which I'm not going to, but if I were to graph it, what kind of shape would it be? It's still a parabola. It's still a parabola. But importantly, it is not the same parabola as this. I mean, obviously it's not the same. But if it's not the same, that means it doesn't have the same greatest height. It doesn't have the same stationary point anymore. Okay? So if all you did was say, okay, slap in this, okay, and then work out how high the road is at that corresponding x value, you will not get the highest point because you've got the stationary point for this guy, not the stationary point for this guy. Okay? So in order to get this a little neater, here's what I'll do. All I want is an axis of symmetry, right? That's minus b on 2a. So all I need to be able to do is rearrange this so that b and a are clear, right? Well, that there, that's a, right? And b is somewhere in here. Now I think you'll get this when you simplify out. Let me just double check. I think that's what I got. Yeah, okay, good. So now if I want my axis of symmetry, I say it's minus b on 2a, which is minus 5 on 72. And you just crunch that out, okay? So you get an x value for this. This is an x value where this is, okay? I think the fraction is something awkward like 408 on 25, okay? That's okay, your calculator handles all of that. What am I gonna do with this x value? I should sub it in, but where should I sub it in? I have like 100 equations that I could choose from. Which one? Just one up the top, isn't it? This will give me the actual distance. It's 9 meters above the road is what I'm looking for. Above the road, okay? So you take this and you sub into the equation of Road. That's a very official acronym, by the way. EOR always stands for equation of road. It doesn't, you're not laughing, you're obviously too tired. Okay, so I'm going to say y equals, I'll slap that in, and then I think you get this. Exactly, in fact. I don't think there are any decimal places because it's a nice number there. Okay, which of course is approximately 9 meters. Okay? Are there any questions so far? Any steps that have been confusing? All right, last bit. We want to show that the time of flight, okay, now it does go back to time, so I'm going to have to go back to them in a second. So the time of flight is 2.72 seconds. That's an awkward number. And find correct to the nearest tenth of a meter how far the ball has been thrown up the road. That's that distance. How far the ball is thrown up the road? There it is right there. Whatever that is. Okay? So, when does the ball finally hit the road? What can we do in this situation? What would be an easy way of doing this to solve it? You've got a couple alternatives, don't you? Number one, you could say, I just want to know when the equation of road intersects with the equation of path. That'll do it, won't it? Okay? And you'll get that value out. However, being that the previous part of the question, I just worked out this distance, right? All I want this distance to be is 0. I want the ball and the road to be at the same spot, okay? So you've got this solution here already for an x value. Can you see that? You see it? So if that's, remember this is the axis of symmetry, right? So this is halfway. So how much further will I have to go to get to the ground? Well, I just have to go this distance again, right? So I would say, this is part C, what am I doing? Part 2. Okay. My x value that corresponds to hitting the road is just double the axis of symmetry. It's this. That is the place horizontally where I hit the road. Okay? That value there. Okay? Now, very, very briefly, I just have to go back to a time equation. What's our time equation? I believe it's x equals 12t, isn't it? We proved that in part A. Okay? So all you do is you say, well, 12t must equal that. So you divide by 12. 252, 300? 300? Is that right? Whatever that is. I think that's right. Where's my calculator? 2.72, hooray! There you go. Okay. Can you see? I know I'm doing a lot of talking, but see how little working and how simple the equations are if the question fits equation of path. Look at this. It's so pedestrian, right? Okay, last part. What do I want to work out? How far up the road it's gone. Okay? I already know this value. It's here. Okay? 816 on 25. You should all be able to tell me without reaching to your calculators how high I am. Come on, look at it. What's the equation of the road? It's x on 5, isn't it? X, 816 on 5. So that should be 125, right? So there you go. That's a vertical distance. You got a horizontal distance. You pull out Pythagoras, and that'll give you the distance up the road. Okay? Which I think, if I do it right, it'll be 33.26 something, 286. Blah, 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 blah. They want it to a tenth of a meter, don't they? Okay. Can you imagine how complicated that would be if you thought about these all in terms of actual time? What a mess, okay? Imagine taking this time back into your original x and y equations and then, oh, my head, okay? So there you go. That's the way I approach it.